Hello and welcome to Friday's edition of Cracking the Cryptic, and a real rarity on the channel today where we are doing plain old killer Sudoku, which I can't remember the last time I just did a normal killer Sudoku on the channel, but this is by a very, very special constructor, Jay Dyer. And Jay's puzzles are always absolutely wonderful. It's called Square Dance, I guess because... well, I think it must be that. That almost looks like it's trying to be a square, but it isn't really. So we've got a square dance going on in the grid, and this is what we're going to be having a go at in today's video. I think this has got 4 stars out of 5 for difficulty. Although I will tell you that we've had a couple of people write in and request this puzzle because they have not been able to solve it. Apparently it is reasonably challenging, but I'm sure it's going to be wonderful. And we'll have a look at it in just a moment or two's time. Maverick has taken off. That has taken how long? 1 minute, 4 seconds. Well done, Maverick. So we're about to get buzzed by a low-flying aircraft. There's not a lot I can do about it. I can't transplant my house anywhere, so we have to put up with Maverick's peccadillos and his penchant for buzzing past my office. Anyway, what can I tell you about today? I'll start off with actually a birthday and a sort of an anticipation of a marriage. Joe, it is your birthday today. I know this because your fiancée Vicky wrote to us and said that other than her, the channel is probably the place that you spent the most, or we're the people you spend the most time with. So Joe, I'm delighted to hear that you enjoy the channel so much, and I know that a year today, I think the two of you are getting married. So you'll be getting married. Being a guy fond of deductions, you're getting married on your birthday next year, which is a lovely thing to do. So Joe, I hope you have a great birthday today. I hope you have a great wedding in a year's time, and I hope on both of those occasions you're able to indulge in an enormous amount of chocolate cake. I don't have any other news, just, well, a reminder that if you enjoy the channel, do check out our Sudoku Club over on Patreon. It's a couple of bucks a month to support us there, and you get access to all sorts of extra content, which really is, it's quite a thing. So I'll try and remember to put a link on the screen, but that's all I've got to tell you. Let's have a look at Jay's puzzle. These are the rules, which are very short for once. Normal Sudoku rules apply, so we've got to put the digits 1 to 9 once each in every row, in every column, and in every 3x3 box. Digits in a cage may not repeat and sum to the indicated total. So those 3 digits sum to 21. Now what you can't do is 885, for example, because those 2 8s, although they don't seem to see each other using the normal Sudoku rules, they repeat in a cage, and that is too naughty for words. Don't let that happen or you'll get the puzzle wrong. The way to play is to click the link under the video as usual. That will take you to a page which looks identical to the one I'm facing here, and you can play the puzzle on whichever device takes your fancy. But now I get to play. Let's get cracking. Now, perhaps unsurprisingly, there are no there are actually no cages that I particularly like the look of in terms of, knowing what their contents are. I think the 5 cage, bizarrely, is the most restricted cage in the sense it only has 2 possible options. So a 5 cage is either a 1-4 pair or a 2-3 pair. But I think every other cage has at least 3 options. I think it's going to be the 21 cages where we have to start, because 21 is at least a bit restricted, and there seem to be, look at that, you can double click on the cages and they all light up, but all of those cages there are all 21 cages, and there are only 3 different ways of making 21 using different Sudoku digits. So you could have 489, you could have 579, or you could miss the 9 out altogether and have 678. So I think what we're going to be required to do here is to somehow colour these between their options, because what I can see is, for example, if we make this a purple combination of 21 cage, can that also be a purple combination? And the answer is no, because these 4 digits would only be selected from 3 different numbers. Let me show you. Imagine this was 489, and we tried to make this also 489. You can see that these 4 digits are only selectable from 3 different digits, and therefore you'd have to repeat a digit in these 4 cells, and that would break the rules of Sudoku. So what we can say immediately is that this is a different flavour of 21 to this. Now, do we also get to say that this is the 3rd flavour? Or could this be... It can't be purple for the same reasons this couldn't be purple. But could it be blue? And the answer is, I doubt it. But let me think about this for a moment. So if it was blue... If it was blue, then this digit would be in one of those 2 squares. Actually, that's given me another thought we could think about. This digit would be in one of those 2 squares. I don't know, actually. I can't immediately see why that can't be blue. One thing I was thinking about, as I was thinking about whether this could be blue, is if you consider all of the 3 flavours of 21 cage, so 678, 579, 489, they always have a common digit. So I was wondering if that might be a better way to think about this. So because there is a common digit between, well, let's use blue. There's a common digit between blue and purple. I don't know what that digit is, but it must exist. And that digit will be ruled out of those 2 squares of this 21 cage, but it could go there. So you can't even say that this cage couldn't be blue or purple. There's a lot of symmetry as well, isn't there, actually? The 21 cages are sort of making an interesting pattern. Sorry about this. I am not seeing it. 9 cage has got 3 different ways of making its total. 135, 126 and 234. Oh, it's not something to do with... Let me just get rid of the colouring there. It's not something to do with where these digits go in box 9, is it? Because you can't put... Yeah, you can't put those 3 digits only in those cages, can you? Because these add up to 21, and these 4 digits add up to 21. So if you put the 3 digits into, say, those 3 squares, that would be a 0. So at least one of these digits has to be in one of these 2 squares. This is weird, actually. This is weird. I mean, I have thought about whether it's Ard's set, because that's obviously shouting out at you a bit, but I don't think it is, because Ard's set is the sort of principle that the difference between that 16 cell region and this 25 cell region is exactly one set of the digits 1 to 9, which the problem with that is that we know so little about, we know quite a lot about the green one, but we know so little about the purple one that I don't think that's going to be relevant, although they are going to be very big, aren't they? And they're quite small. It might be worth thinking about. I don't think it is going to be important. So the difference between green and purple is 45 still, using the secret. I will explain this if I can. If I think for a moment this is relevant, I will explain some of what I'm doing here, but I'm just thinking about it at the moment and probably going to move on. So the absolute minimum value of green would be if I make this an 8-9 pair, which is 17 minus 63 is 46. So 46 plus 45 is 91. So 91 is the minimum value of purple. Those squares add up to 21. So the minimum value of these squares is 70. That is quite high. That is quite high. Oh, goodness me. Right, okay, right, we are going to have to do this, I think, because I mean, that is just quite high. I mean, I could make those 30, I could make those 30, but I'd still have to make those 15. And that's on the basis this is minimum. Good grief. Right, Jay. You naughty, naughty constructor. Right. So, what on earth was all that about, I hear you say? Well, I mean, it is a good tip. If you ever see this sort of pattern where it looks like it's isolating either this shape in the grid or this shape, of course, you know, other possibilities are available. You could be looking at this 4x4 and that 5x5. There is an equivalence that you can draw, and it's very simple to understand. Let's just highlight those 4 rows of the grid. We know exactly what digits in total we will find within those green cells, don't we? 4 sets of the digits 1 to 9. There will be 4 4s, 4 5s, 4 1s, 4 9s, etc., etc. Well, let's also highlight the final 5 columns of the grid. Boom, like that. So we know that this is 5 sets of the digits 1 to 9 in yellow because it's 5 complete columns. So the difference between the contents of the cells in green and the contents of the cells in yellow is 1 set of the digits 1 to 9. Now, if we were to remove this square from green and yellow, what's the difference between what's left in green and what's left in yellow? And this is the crucial point. Well, it's still 1 set of the digits 1 to 9, isn't it? Because if the difference between two things is 1 set of the digits 1 to 9, and then I take the same thing out of both of those things, the difference between them remains constant. So I can take all of these squares, which appear in both green and yellow, out of green and yellow, and we get that the difference between what remains in green and what remains in yellow is still that 1 set of the digits 1 to 9 that was the difference when we had the 5 columns versus the 4 rows. Now, but we can start to extend this logic, because if the difference between these things is 1 set of the digits 1 to 9, if I was to remove the whole of box 1 from green and the whole of box 9 from yellow, I'm removing the same thing from both sets again, because box 1 is just 1 set of the digits 1 to 9 and box 9 is just 1 set of the digits 1 to 9. So still the difference between green and yellow is still 1 set of the digits 1 to 9. And now we have to convert to mathematics, because there is a secret that I tell only my very favourite people. If you're still watching this video, you're definitely one of my favourite people. And the secret is that 1 set of the digits 1 to 9, if you sum up the digits, you get 45. So the difference between green and yellow is 45. But we can still even go further than this, because how can I sort of get an idea of what those green cells sum to? Now what I did was I made those as big as I could in my brain. I made those 8, 9. They could be much lower, but they're a maximum of an 8, 9 pair. And that means the absolute minimum value of the green digits is, I think, 46. Let me do that maths again, because what I did was I said 3 lots of 21 is 63. Minus 17, that is 46. So this is 46 at an absolute minimum. And that means the absolute minimum value of yellow is the green digits, which are 46 at least, plus 45, one set of the digits 1 to 9, which is the difference between green and yellow, which is 91. So the absolute minimum value of yellow is 91. But those squares are indisputably valued at 12, and these are indisputably valued at 9. So those 6 cells are valued at 21. So these squares have to be at least 70. And if these are not an 8-9 pair, they have to be more than 70. So yeah, more than 70. Oh, hang on, I'm wrong then. I've got the wrong number. Sorry, when I did this, I thought these had to be big. They don't have to be big at all. I've done the maths wrong. Oh, this is not... So I've just wasted 15 minutes of everyone's time because this is not right. Sorry. 46, 91, 70. Yeah, this is wrong. In my brain, I got 75. And that's not right. So I thought these had to be 15. But the fact is, these could be 30, these could be 30. And the minimum value of these is therefore only 10, which isn't absolutely neither here nor there. Oh, I'm sorry. I'm sorry. Bobbins. Oh, dearie me. I don't think there's any value in taking that forward, is there? The only point would be I don't think that's going to be either. I'm just going to think about the bottom 2 rows quickly. Just because these all look like reasonably chunky numbers to me. So what have we got here? We've got 31 plus 39, which is 70. So the maximum value of those squares is 20. So I can't make these add up to 30 then. Sorry, Maverick's getting lower and lower. Am I going crazy? Sorry, I've changed tack. I've sort of changed tack altogether now. What I'm thinking about now is whether, because in order to get to the 70 that I think has to be the minimum total of these, how many? 10 squares. I think those squares have to add up to at least 70. Now in my brain, what I'd done is I'd gone, okay, if these were 6, 7, 8, 9, that's 30. If these are 6, 7, 8, 9, that's another 30, which means the absolute minimum value of these is 10, which is not a very interesting number. But I'm not sure these can add up to 30. Because the blue squares actually sum to 20. And the way I've got to that, so this is all a bit confusing today, but I'm looking at the bottom 2 rows of the grid and I'm saying, okay, well, by the secret that we talked about earlier, the sum of the digits 1 to 9, these squares are 45 and these squares are 45. So that's 90, isn't it? Now, my calculation of the value of those cages is that they summed up to 70, which means these sum up to 20, which is not that much. Yeah, yes, okay, so we can do this, because now the minimum value, yeah, I want to max these out. The minimum value of those squares would be a 1 here, a 1 here, and a 2 here. That's 4. So the maximum value of these remaining blue squares is 16. And the maximum value of this square is 9. So the maximum value of these squares here, those ones, is 25. So 25 plus 30. And now I can get back to 15 here. Bingo. That is bizarre. That is bizarre. So, well, it's good. It's good, but it's bizarre. Because what we've actually proved now is what I thought I had proved by a much simpler method about 10 minutes ago in the video. I've proved that these squares have to add up to at least 15. Because I am saying now these can't add up to more than 16. So this can't be more than 25, this can't be more than 30. So these have to be at least 15, which I think means that they have to be 6, 7s, 8s and 9s. And there is pressure here. There is pressure. It was worth doing. I'm going to claim that at least. I mean, admit some of you might say it's still clutching at straws. It is a bit, because I'm not sure I'm getting much more than this out of it. Oh, okay. Sorry, that was a message on my phone. I might have to deal with that. Oh, let me just see if I can make another deduction before we stop, though. So I need. Well, so there isn't a massive amount of freedom. Actually, in total, there's just not a lot of freedom, is there? Or am I going crazy? The absolute maximum I'm saying that these could add up to is not that different from what I just did. Yeah, it's not. It's not. Yeah, okay, so this is the point now. And this might be the better way of thinking about it, is actually the maximum value of that is 30. The maximum value of that is 25, so that's 55. And the absolute maximum value of that is 17. Which is 72, isn't it? Plus 21 is 93. So there is no way that I can make the green squares add up to more than 93 minus 45, which is 48, which means these squares have to add up to a big total, because these altogether add up to 63. So I'm saying these have to add up to at least 15. To get this down to a maximum of 48, which this can't be any greater than. Wow, okay. So, right, I've got two degrees of freedom, is what we're saying. So either this is 15, 16, or 17. And either this is 15, 16, or 17. And this can be 30, 29, or 28. And we've got 2 degrees of freedom here. So this can't be lower than 7. And these 3 squares, which allowed me to get these up as high as 16, I can't make these so big that this falls in value to lower than 14. So what was that? What was I doing? I made these 1, 1 and 2, which are adding up to 4. So I can make them add up to 6 in total. That will still work. So this is at least a 1 and a 2, so that can be a 3. And I can make them add up to 6 in total. So these can add up to 5, because this could be a 1. So these are from 1, 2, 3, and 4. And this could be a 4, 1. And this could be a... Yeah, because if that's a 1 and that's a 1 and that's a 4, I think the world will still add up. Okay. So what does this mean? I haven't got a clue. Not got a clue. This is adding up to at least 28. So it does have to have a 9 in it, doesn't it? And an 8, I think. Because if it didn't, let's say it didn't have 9 in it, its maximum value would be 8765, which is 26. If it didn't have 8 in it, its maximum value would be 9675, which is 27. Neither of those is 28. So this has 9 and 8 in it. This digit is, well, it's got to still be in a 21 cage, so it's 4, 5, 6, or 7. Wow. I mean, it's fascinating, and there is some sort of equilibrium between green and yellow, but it doesn't seem to be quite enough, does it? Sorry, I haven't got it. I don't. Presumably we can. I don't know. I'm not even sure where to look, actually. I tell you one thing I hadn't thought about. Look at that column from the perspective of very low digits. 1s, 2s, 3s. Oh, that's rotten. We can nearly do that. That's really close. Because it's almost, if you look at those 4 squares there, they're the only positions 1s, 2s and 3s can go to for in the column. And that bottom cell there, well, if that was a 1, that would make this 2, 3, that would have to be a 1. Because we know that these blue squares can't add up to more than 6. That would be a 9. 1, 9. This would be an 8. It's probably fine. Oh, hang on a moment, because the same thing is true there, apparently. Oh, it's okay, so is this... Oh, no, I think I might have messed this up. I think I might have led us all on a wild goose chase. This might be about low digits, actually. A 9 cage has got to have 2 low digits in it. Oh, no, hang on. Well, so... 2, 3, 4, 5. Yeah, okay. Could we have done everything I'm about? I think we could. I don't believe it. Okay, so what I'm noticing now is that I know that the purple squares contain the 3 digits 1, 2 and 3 in row 4, because you can't put 1s, 2s and 3s in 21 cages. So purple contains 3 digits from 1, 2 and 3. Now look at the 9 cage. How many digits from 1, 2 and 3 does that have in it? It must have 2, because whether it's 1, 2, 6, 1, 3, 5 or 2, 3, 4, you always get 2 low digits. That's just a feature of 9 cages that I've learnt over the years. So these squares plus this cage here contain 5 of the digits 1, 2 and 3 which appear in these 2 boxes. Well, there are only 6 digits. There are 2 1s in these 2 boxes, 2 2s and 2 3s, because it's 2 3x3 boxes of a Sudoku. And 5 of those digits are in those squares. None of them are in there, none of them are in there, because this, remember, adds up to 28 at least. So it cannot have 1, 2 or 3 in it. These can't have 1, 2 or 3 in it. Now, that means that this domino here can have a maximum of 1 of 1, 2 and 3 in it. But we know that overall, orange contains 3 of the digits 1, 2 and 3 in this column. So these 2 squares are from 1, 2 and 3. And one of these is a 1, 2 or 3. Don't know which one. So let's put it in like that. And then whatever this is, oh no, we don't know. I was going to say we know. Well, we do know it's in one of those two, I suppose. So we do know whatever this digit is doesn't appear in the 9 cage at all. So this is the un-9 cageable digit. Now this digit is now low in an 18 cage. Which means that this digit is quite high, isn't it? That's at least 6 again now. Which feels like it's trying to be interesting. And the worrying thing is... I'm not sure, yeah, I think my green and yellowing has not really... I suppose maybe I needed that to tell me that those had to add up to enough. I'm unsure. I've got a horrible feeling that this was all doable without using any of the hard set theory that we did. Right. So... So how do we go any further than this then? That is the next question. Do we know? Do we know? Oh, I'm sorry, I haven't got this yet either. How do we get more of... Oh, see, we've got the 5 cage up here that might be coming into its own as well. Golly, this is clever, isn't it? It really is clever. This digit has got to be in one of those two. It doesn't appear in the 9 cage at all. But is there some restriction here? Looks like we're trying to get towards some sort of triple in the bottom row, but I mean it is hard for one of these to be a 4, because I think we have to double 1. Well, for either of these to be a 4, you have to put double 1 into those squares, because these can't add up to more than 6. So there might be a technical reason that doesn't work. If you do that, what's the result of it? Does that make that a 1, perhaps? Or could you still have a 1 in the 12 cage? We've got to still have one of the digits 1, 2, and 3 in one of these positions. Now, how many of those digits? If there's no, there must be a 1, 2, or 3 in a 12 cage, because otherwise it would contain 4, 5, and 6, wouldn't it? But I can't make this a 1, 2, or a 3. That's fascinating. Right. Yeah, I don't think this is anything to do with hard set. I really don't. Okay, so what I'm saying now is that when we did our count of 1s, 2s, and 3s in boxes 5 and 6, we worked out that there were 2 in there and 3 in purple. So there was a maximum of 1 in this domino, but there had to be 1 in this domino, because there has to be 3 in orange overall, and I could only put 2 of those in box 8. So there is no, this digit is not a 1, 2, or a 3. I don't really know how to show that, but I mean, well, let's show it in a ludicrous way, like that. That digit is one of those. Now, imagine that there is no 1, 2, or 3 in either of these digits as well. Well, then the minimum sum of this would be 4, 5, 6, which is 15. That's many more than 12. So there is a 1, 2, or 3 in one of these squares. And therefore, these blue squares here don't contain any 1s, 2s or 3s. Because I've got the 1, 2, 3 triple in box 8. That means, and these added up, I want to say these added up to 16 as a maximum. Well, now their minimum is 15 because they can't include any 1s, 2s and 3s. So they are either, they're a 4 and a 5 and either a 6 or a 7 as their extra digit. That's the only way they can be made up. But now, if this is adding up to a minimum of 15 and a maximum of 16, but we know overall blue adds up to 20, what are these digits now? Because even if these are 15, these have to be, they can't involve 4 anymore. That's definitely true. So there is definitely a 1, 2, 3 triple in the bottom row. There has to be a 1 in here. Because otherwise we're adding up to 6 again. It's too many. I can add them up to a maximum of 5. If that's a 3, these are a minimum of 1, 2. It doesn't work. So this is a 1 or a 2. If this is 2, this has to be a 1, 2 pair. So it would be double 2 here, with this being a 1. This would be a 3. If this is a 1, these could be 1, 2 or 1, 3. So this has got 4 and 5 in it. And the digit, so we can limit this, I think, now. Because the digit in here, which is low, could be as low as 1. But the other digit, the next digit that you can have in it, because we've then used, say this is a 1 in here, then this is a 2, 3, this has got 4 and 5 in it, so the next lowest digit here is a 6. So this is a minimum of, this adds up to an absolute minimum of 7, which means this digit, which can't be 1, 2 or 3, is 4 or 5. And the digit that's in here with, I don't think you can put 3 in here now, can you? Yeah, because it would blow up, it would get too big. So there is definitely a 3 in one of these. This has got 1 or 2 in it. So it's a 1 or a 2 that's missing from the 9 cage. The 9 cage must have a 3 in it. Because this digit has to appear in purple. So it's in one of those two, and therefore it's ruled out of the 9 cage. So this 12 cage, these digits are either 1, 6, oh I see, it's 1, 6 or 1, 7 or 2, 6. So these are the options for this cage. Which means between these 5 digits include the 6 and the 7. Which means this square is not a 7 anymore. Which means this is an 8 or a 9. Oh, don't tell me, have I done it again? I have done it again, haven't I? That would have been a way of looking at this holistically and just saying where are 8 and 9 in box 8. That's probably been available. I'm doing this puzzle in totally the wrong way. I know I am, but I still love it. It's still fascinating. I just think I could have done it more efficiently. Alright, so now what? Because I know that this is 15 or 16, that's not changing the pressure up here. That's not changing the pressure up here. This digit is in this, so this digit is in one of those 2 digits. So I've got a 1, 2, 3 triple in the bottom row. Is that telling me anything useful about the world? Where's, oh, nearly. That's really nearly true. Where's 5 in the bottom row? You can't put 5 in a 2-cell 10 cage because the other digit in that cage will be 5. So either this is 5 or this is 5. Now if that's 5, what's that doing? Anything or nothing? If that's 5, that's 6. Is that doing something here? 6, 7, 8 would be ruled out. But it could still be 5, 7, 9 or 4, 8, 9. Sorry, trying to work this out. How do we do this? I don't know. If we put... I don't know. I'm playing around with the digits in these rows. I'm sort of something I've noted, obviously, and it's probably obvious anyway, is that those top digits there in the 10 cages can't be too big because they're going to put 1s, 2s and 3s beneath them. So these digits here are either very low or on the low side of 10 or below 5, or they're 6. That's the only options. So maybe it is worth just thinking about that. So we've either got a 4, 6 pair or a 7, 8, 9 in these positions. I think all I'm proving here is what I thought I was proving before. Which is to do with the position of 5 in the bottom row. But I'm not sure about that. There might be more we can do here. There might be more we can do. I think there is stress. Might be to do with where 8s and 9s go in this. No, because we could put one here. We could put one here if it was there. Yeah, but we can only have one in all of these, can't we? Because we haven't got enough low digits. So there is definitely an 8 or a 9 in here. Which means either there's an 8 or a 9 in here, which would make this 4, 8, 9. Or... can that be an 8 or a 9? That would give us a 1 here. That's probably quite likely. Then that would be a 2. This would be a 3. Okay, this is challenging. This is definitely challenging. I wonder if there's a way of proving... There's certainly no 1s, 2s and 3s in these squares. Because the only way I don't use up a 1, 2 and a 3 in this domino is making it a 4, 6 pair. And if I make that a 4, 6 pair, this can't be 5, 6. So it would also need a 1, 2 or a 3 in it, or specifically a 2 or a 3 in it. So there would be a 1, 2, 3 triple here. This would be 4, 6. There would be a 7 in one of these. There's definitely got 4 and 5 here, haven't we? Oh, it's so close, I think. Well, I wonder, I don't quite know how to do it though, if I'm honest. I'm not sure what it is I'm meant to be grokking. And I do know these have to add up to quite a lot, at least 15 and possibly as much as 17. Maybe There's no problem there. If this was 9, 8, there would be a 9 and an 8 along here, so this would be a 9 or an 8. Yeah, everything is teetering on the brink of being too difficult, but still retaining its ability to work. There must be an 8 or a 9 in there, mustn't there? Because if there wasn't, this couldn't add up to enough. So that 8 or a 9 there is going to pair up with the 8 or the 9 there and put an 8 or a 9 in one of those squares. Now if I knew it was in the bottom position, I would know this was a 1, 2, 3. And this would be 4, 7 or 5, 6. Now, is that useful or not? I don't know. I'm not sure, sorry. Could be to do with... Is it to do with these digits then? I don't think it is. I don't think it's likely to be, but let me just mull that for a moment. I mean, if this was 8, 6, 7, then these become a 4, 5 pair, don't they? And 9 can't go any... Oh, that can't work. You can't put 9 in the row. Oh no, you could. It could go, sorry, it could go there. Because it would have a 2 beneath it. Oh, so maybe that's right. I don't know, it's very constrained. So I'm saying if that's 6, 7, 8, this becomes 4, 5. No, it's still... No, I don't think it does work, actually. Although that's very complicated. So what I'm claiming is, let's actually do it slowly. If this is 6, 7, 8, you can see this becomes a 4, 5 pair. But now neither of these can involve 4 or 6, because 4 and 6 have gone from the row. Which means this digit is low, which means this is a 1, 2, 3 triple. And the only place for 9 in the row is here, and that would have a 2 beneath it, and there'd be too many low digits, so it doesn't work. So actually, we now learn that there is a 9 in this sequence. I don't know where it goes, but there is. So it could be 9, 8, 4, couldn't it? Now if it's 9, 8, 4, what do we then learn about the world? We would know this was a 4. That's quite interesting as well, actually. Because I know there's a 4 and a 5 in here, I think it's more likely this is 9, 5, 7, actually. Because I feel like if this is 4, 8, 9, because this becomes a 4, I'm then again removing 4, 6 as a possibility from these 10 cages. And that I'm not saying it's impossible to do that, but I'm saying it feels like that's a problem to me. It's just an inkling rather than a logical deduction. Let me think about that for a second. So if that's 4, 8, 9, that's a 4. That's either 5, 6 or 5, 7. The only place 5 could go is there. That's the only place 6 could go. And that might work. Ah, that's a shame. Okay. So if on the other hand we go 5, 7, 9, then this becomes a 5 then. Hang on, that's more constrained. Because this has to be 4, 6 then. And again I can't put 4 or 6 in any of the 10 cages. 6, 1, 2, 3, 1, 2, 3. So what? So what's the point there? The point is that becomes an 8, which it can't be. Yeah, okay, that doesn't work. It's really complicated, but it doesn't work. Okay, so what I'm contending now doesn't work is if this is 5, 7, 9. Let's just put it in and have a look at it. Oops. Okay, so what I'm saying now is that these squares are left to be a 4, 6 pair. And this has to be a 5. And you can see, if we look, because this has become a 4, 6 pair, you knock 4 and 6 out of both 10 cages, which means that this is definitely a low digit. But where do we put 8 in the row? We have to put it here. This would be a 3 beneath it. But this is a low digit, remember, it's a 1, 2 or a 3, so there's no way that this can be that. So in actual fact, what we're being told all along, although there may be an elegant way, a more elegant way than I'm finding to see it, what we're being told is that this, which we worked out had to have a 9 in it because it couldn't be 6, 7, 8, now is not 5, 7, 9, so it is 4, 8, 9. And if it's 4, 8, 9, we can take 4 out of these squares, we can put 4 into this square, which is, that's our first digit, believe it or not. That is our first digit. So these lose their ability to contain 4s, which means we can take 6 out of both 10 cages as well. This is going to be the thing that we earn out of this. And now this digit is 5, 6 or 7. But it's not 7 because that would be a 4. So this has become a 5, 6 pair. And that's lovely, but is, well, actually, no, there you go. I've got a 7, 8, 9 triple in the bottom row that's just come out of nowhere, so that's got to be a 6. That's surely constraining. That's a 6, that's a 5. These two squares have to add up to 12, so they have to be 3 and 9. Ah, we don't really want a 9 there, because we were trying to make that, you know, we were trying to restrict this, weren't we? So 9 comes out of these, which means 1 comes out of these, which means there's a 1 here now. So if this was 2, we go too high. We can't make this add up to 6 anymore, I didn't think, because this would only be 14, and 14 and 9 is 23, and it wasn't enough. So this is a 1, which we could have actually seen by Sudoku, I'm now seeing. That's 2, sorry. Oh no, so we got 4, which means these do add up to 16. Which means these add up to 12, which means they are 5 and 7. So this was maxed out, which is, well, I mean, it's fine, but it's not what we were hoping for, because it would have been more constrained had it not been. Okay, so this digit now is 1 or 2. So it's sort of a 1, 2 pair notionally here. There is a 6 in here. So it's either 7 or 8. We still don't know, do we? This is a 3 by Sudoku. We're going to get most of the bottom row filled in, believe it or not. This is an 8 by Sudoku. So this over here is a 4, 9 pair. These squares are 4, 8 and 9 as well. We don't quite have roping, but it felt like we might be heading in that direction. 3, 5 and 7 go into these squares. This is not, oh, that's not 6 anymore up there. Is that doing something? This is not 5, 6, so it's either 9, 2, 3, 8, or 4, 7, which is all very well. I don't think it's very helpful. Alright, I'm going to claim it's not 3, 8, this. I think that's reasonable. And that the reason for that is, how could there not be an 8 in either of those squares? If there's no 8 in either of these squares, then because there's no 8 in those squares either, both of these have to be selected from the 5, 7, 9 option. And we know that's going to break the top of there. There is definitely an 8 in one of those. So this is not 3, 8. It's either 4, 7 or 2, 9. So these squares now include so if that's 9, this is 4, 7. If this is 4, this is 9, 2. So these digits include 4s and 9s. So that digit can't be a 9 anymore. If that digit can't be a 9, that digit can't be a 6, can it? Because didn't we work out these two had to add up to at least 15 and possibly as much as 17? So now this digit is not 4, 9 or 6, so it is 5, 7 or 8. So if that was a 7, 8 pair, we would know the total of those squares. They would be 42 minus 15, which is 27. 27 and 11 is 38. These would be adding up to 7, they would be a 1, 2 and 4, and there would be a 4 here, and that would give us this digit, which would be very useful. In fact, that's a problem, isn't it? Yeah, that's a problem with this being a 5. If that's a 5, you can't make this total. It'll break. It'll break these 3 squares, because if that's a 5, even if I make this an 8, which is the most I could make it, these are adding up to at most 13. But 13 minus 42 is 29, and these can't add up to 29 because there's no 8 available. And it's even worse if it's 5 and 7, because then it's 30 here, and there's no 8 available. So this is not a 5. This is a 7, 8 pair. Right, so this isn't 7. So it's not 7, 4. It's 2, 9. This is a 4. This is a 9. This is not 7. So it's 1, 3 and 5 into these squares. These now, let's go back to it. We worked out these added up to 27, didn't we? Have I gone mad? 42 minus 15 is 27. So this is 27 plus 11 is 38. Therefore, to make 45 in the column by the secret, these add up to 7, which means these are from 1, 2 and 4. There's a 4 in here, which makes this 5, which means these add up to 7, which means they're 1 and 6, which means this is a 2, which means these are a 1, 4 pair. And as Maverick buzzes past, this is a 5, this is a 7, this is not 7, this is not 9 either, actually. We don't necessarily know what they have to add up to yet, at least I don't think we do. So, there is definitely a 5 up there, so one of these cages is 5, 7, 9. Oh, that got really exciting for a moment, didn't it? We got a flurry of activity. What else can we do? 3. I worked out there was a 3 in that 9 cage. It's got to go here. I'm now realising that's probably been available for ages. So that okay. So where's the 3 in row 4? It's got to go here. So that's a 3. We're getting all sorts of 3s in the grid. Good grief. That's not a 3 or a 4 actually. Well, 1 has to make an appearance in purple, so that is now exactly there, which means there is a 2 in one of these squares, and of course I don't know where it goes. 1 is in one of those squares by Sudoku. These squares are not 1 and 5, so these must be a 2, 4 pair. That's interesting, because where's 4 now in this row? Because that's not 4 anymore, is it? So 4 is in this cage, which means this is from 4, 8. This must be the 4, 8, 9 cage, or a 4, 8, 9 cage. it's got to have 8 in it. So that's actually placed. That's got to be here. That's 9. That's 4. There we go. That's now 7, which means that's 8, which means they can't have the 5 in there because the other digit would have to be another 8. So this is 5 and 9, which is lovely. I mean, in fact, we know the order, so let's not mess about. It's got to be like that. Now, this column needs 6. Oh, see, it's 6, 7. So, no, that's bad news. That's bad news. The reason it's bad news is that means that these cages are all different, which means there might have been a way of me proving that from the start as well. Oh, goodness. Oh, well, never mind. At least we're still, I think we're still in the game in terms of solving the puzzle. And that is something for which we should be thankful, because I don't think this is an easy puzzle, even though I have a strong suspicion that there might have been a more, well, a path with more alacrity to it. Let's put it like that. Now that's not 7 anymore. So these are so 5 in the row has to go here. So this is now another of these 5, 7, 9 cages. 9 is here, so 9 is not here, so 9 is here. This is a 4, 8 pair. In this column, these squares are from 4, 6, and 8. We can do the 9 and the 7 by Sudoku of all things. We can do the 9. How many 9s have we got? Lots. Not all, though. Lots, but not all. Okay. We have now identified the nature of all of the funny cases. Look, this is a 2, 6 pair. That's quite handy, because that's going to make this an 8. Now, that's huge. Right, that's got to be big, hasn't it? Because now this is 15 as a maximum. I think that we could only do that if we made that add up to 30, which it now does. I'm now noticing. Oh no. Oh, that's rotten. So I've got that deduction and it doesn't do anything. Okay, if that's 6, 8, that's a 4, that's an 8. So we need 1, 2, and 4 in this column, which means we need 5, 6, and 8 here. That's not 8, that's not 5. Oh dear. Okay. So, where does this take us? This is 7. This is 9, this is 9, this is 2, this is 2, this is 4, this is 4, this is 1. That's 8, that's 6. I mean, it does seem to still be gradually revealing its secrets to us, doesn't it? 3, 6. That's not 5 anymore. This don't include 2. Can I do this? Can I do either of these digits? Of course not. Don't be ludicrous, Simon. What about 8? 8's got to be there in that box, which means that's 8. Which means I've got to put 6 somewhere in this row, and it's now got to be here. So that becomes 6, that becomes 3. Do we know what this is yet? Don't know. I've got 23, 35. These have to add up to 10. So these can't be a 1, 3 pair, because that would make that a 6. So that must be a 5 by that logic, which means these add up to 5 as well, which means this is 2 or 4. The 5 does a 5 here and a 6, 6, 7. Now there is a 7, look, in my 12 cage, which is unsurprising, because the other pair that don't add up to 5 must have gone in here. So I could have worked that out a different way. No. Oh dear. So what's going on then? 1. I feel like, this 1 is doing work. I didn't see it, probably because I've changed the colour of it. So this is a 2, 4 pair at the top of the grid. But that means that's got to be the 7, which means this is a 1 or a 3, and it can't be a 1. So it's 3 there, 2 there, 4 there, 1 there, 2, 3 into the 5 cage, 4 here, 2 here, 1 here, 2, 6, 6, 1, 1, something, 4, I think, 3, 5, boom. Wow, yes, I've done it. That was an amazing puzzle, and one I have rarely done a puzzle on this channel that I feel like I've missed the trick. It's not that I mean, don't get me wrong, I've got to be very careful how I explain what happened during that solve, because I feel like I've let Jay down there, because I know I've solved the puzzle, but I think I've done it in the most peculiar way. I suspect I didn't need the whole green-yellow shading thing, and it was about low digits, and possibly how they then interacted. To the extent I did need the green and yellow shading, again, my sense was, yeah, I mean, that stuff I was having to do at the bottom to understand what the nature of this cage was, I'm sure there must have been a way of doing that was more elegant as well. Because this is a Jay Dyer puzzle, and Jay lives in an elegant world. And I just felt what I did there, I just couldn't see it in the way that I was meant to. I know I couldn't. I'm just convinced. I'm convinced there was a way of seeing this in a more beautiful way. I think it was probably to do with the 10 cages. Or it could have been to do with the fact that I've totally missed the point. So I will look forward to the comments on this one with eager anticipation. I would urge you please to be kind. It's not, we do these solves live, and therefore they are very often imperfect things. And I do feel a small measure of pride to get through that. I don't think it was easy. I certainly don't think it was easy the way I did it. Let me put it like that. It wasn't easy the way I did it. But as I say, I look forward to the comments. Thank you very much for watching and spending your Friday evening with me. And we'll be back later with another edition of Cracking the Cryptic.